Hello guys, today we're going to look at the second half of section 1.1 functions. Now we're going to go over the actual definition of a function. Many students kind of understand what a function is, some of them forget, but a function pretty much is a mathematical relationship in which each input is associated to a single output. Each x has a single y. Think of it like a bank account. If you go to a bank and you give one input, your bank account, hopefully you're only gonna get one output, your bank account, not somebody else's, unless that other person has more money than you. Then good job. Pero each input has a single output. Your personal identification number, your license number, your car's license plate. Whenever somebody searches your license plate, there should only be one answer coming back. So that's like the actual definition of a function. Each input has a single output. Now, there are a couple of ways to visualize this or to mathematically express this. So let's go over visually. Now, always remember one thing. The input, or x, are the possible, the domain of the function is all possible input values for which there is an output value, or all possible input values that make sense. So for example, as you should know, we saw this previously, 1 over x. If I do 1 over 0, I end up with something that is not a number, nan. So the domain would be everything except 0, because 0, you can just say it doesn't make sense. You'll end up with not a number. When you plug this into your calculator, Profe, that's error. That's error. No, that's not error. That's just not a number, and the calculator cannot compute that. But domain, pretty much, is all possible values that exist for that function. Another way you can view it using your calculator is if you have a function and you plug an x value and you get an answer back, which is an actual number, then that means that is part of the domain. If you plug in a value and you get back error, that is not part of the domain because it can't be computed. Normally, we will see limitations in the domain whenever we have variables in the denominator or when we have square roots. Because even though you can work with imaginary numbers, we've already done that, imaginary numbers are not part of the domain, okay? Only the real numbers are expressed in the number line. So those are pretty much the two parent functions that have limitations in the domain. We'll see piecewise functions later, which domains are limited, but when you're thinking of just straight up parent functions, that's why when we look at the parent functions, the square root begins at the origin and looks like this, because you can't actually plug in negative values of x because you won't get a real answer back. That's why it looks like this. And also when you have the rationals, there is a reason it looks like this. The 0 value doesn't exist. You can't plug it in. And we'll talk about that behavior later. But besides these two parent functions, no other parent function has a limit in their domain. These are only two parent functions that have their domain limited: square roots and rationals. Piecewise functions do have set domains, and we're going to go over that when the time comes. So again, there are a couple of ways, going back, just getting back to functions, there are a couple of ways we can visually recognize functions. The easiest is graphically. Remember the vertical line test. Okay. This would be a piecewise function. This would be, just all the parent functions that you know. Well, not all, a couple. Now, in all of these, if we go over the vertical line test, I hope you remember, vertical line test is you draw a vertical line across all the points you can feasibly imagine in that function. If that vertical line ever touches the graph twice, and by graph, I mean the actual graph that you're drawing, not the x and y axis, remember, please. If it touches more than once, then that is not a function. I'll give you a couple of examples of that. So for example, here, if I just draw multiple vertical lines, you can see that these vertical lines only touch my graph once. Here, if I draw vertical lines, they only touch the graph once. Teacher, but there are some gaps there. Doesn't matter. That has nothing to do with whether you're looking at a function or not. If the vertical lines only touch once, you're looking at a function. Nothing else matters. Metallica song. Awesome. Here in the constant, vertical lines. Only touch once. Function. Oh my God, look at this weird shape. Doesn't matter. Vertical lines, it only touches the graph once, and you're done. Now note, some shapes, and this could be kind of tricky, some shapes might look like a perfectly vertical line, like exponential growth, or when you're looking at rationals, when you're looking at very close to your y-axis, but that is not a perfectly vertical line. That is a line that moves incredibly slow to the left. I mean, it moves just by infinitely small numbers to the left, smaller and smaller each time, but it's not a perfectly vertical line. So you can draw an infinite number of vertical lines, and you're only going to touch your function or the graph once. So those are functions. Let's give you guys a couple of graphs which aren't functions, and then I'll explain the whole vertical line thing. So let's say, for example, these expressions. Again, a sideways parabola. We saw those last year. A lot of fun. Crazy symbols. I saw that one twice. I don't know why. Again, vertical line. I'm touching twice. No good. Vertical line. I'm touching more than twice. Even worse. Oh, look, it only touched once here, but here I touched 3 times. Not a function. Sideways parabola. Not a function. Again, don't confuse an equation with a function, because again, you can have a circular equation, but a function is a specific relationship in which each x value only has a single y value. So if I were to draw a horizontal, my coordinate axis here, and let's say this were x equals 3. If I tell you x equals 3, what would the answer be? You would have to say, well, this value and this value. So for that one input, I would get 2 values back, not a function. Okay? Doesn't matter if the value, this is another common question. Profe, but all my answers point to 3. When we're looking at Venn diagrams, we'll see it right now in a second. Doesn't matter if the y is repeated 1 billion times. Does not matter. If you plug in an x and you get just a single value back every time, that's a function. Doesn't matter if that one value you get back is repeated 3 billion times. Doesn't matter. So again, when we're looking at a graph, you can easily recognize a function doing the vertical line test. Pretty simple. Now, when you're looking at a table, all you have to look at are the x values. So let's say, for example, I have 1, 2, 3, 4, and I have 6, 6.5, 7, 7.5. This one has a single output. This 2 has a single output. This 3 has a single output. This 4 has a single output. No problem. Let's look at another table. 1, 2, 3. This is a different equation. 1, 1, 1, 1. Oh my God, the 1 is repeated. Doesn't matter. This x has a single value. 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 Doesn't matter if it's repeated. That is also a function. When is a table not a function? When this happens. Let's say, for example, I have this. A 1 will give me a single value. But look here, when I plug in 2, I'm sorry, I do have to change it. When I plug in the number 2, now 2 could be either a 1 or a 3. Now that single input, 2, even though you see it twice in the table, it's still considered the same input, the number 2. I plugged in the number 2, and I could either get a 1 back or a 3 back. I don't know which. Not a function. So when you're looking at a table, you only really have to focus on the x value to see if there are any x values that are repeated. If there are x values that are repeated and they have different y values, not a function. Again, like the mistake I did, if for some reason you see this, well, no, that is a function. Even though this x value is repeated, when I plug in 2, I get 1, but that's probably a typo or somebody who does not know how to properly build a table, because you would not have to even repeat that value. So that whole look at the x values and if they are repeated, it's not a function. Okay, well, most of the time. But, if this happens, that's still a function because, again, the number 2 will give me only a single output, 1. So in this case, this would not be a function, or this would be a function. If you get 2 different outputs from a single number, it would not be a function. Okay? Function, not a function, because 2 can give me 2 different answers. So that's how to recognize when you're not looking at a function in table form. Now, in the last one, let's look at Venn diagrams. Venn diagrams, not sure if you remember, you have like set A and set B. And let's say, for example, 1, 2, 3. And here I have 6, 7, 8, 9. Let's look at this particular Venn diagram. The 1, the 2, the 3. 1 has a single output. 2 has a single output. 3 has a single output. Function. Pretty simple. Let's see what happens now. The 1 goes to the 6, the 2 goes to a 6, the 3 goes to a 6. Profe, they're all going to the same number. Doesn't matter. Remember, does not matter. 1 has a single output, 2 has a single output, 3 has a single output. You're looking at a function. When would a Venn diagram not be a function? 1 has a single value, 2 has a single value. 3 now has 2 possible values. 3 could be either 6 or 3 could be 8. Not a function. Pretty straightforward. So again, when you have multiple outputs per single input, that would not be a function. Let's look at a everyday term. For example, if I ask a student, when is your birthday? Then they would come up with a single answer. So if I ask that question, when is your birthday? And they give me a single answer, that would be kind of like a function. But if I reverse the question and I say, who was born December 30th? Multiple people can be born. So in this case, the whole birth date relationship would not be a function because this single input, when were you born, gives me multiple answers. That would not be a function. If I were to say, when were you born, and I get a single input, boom, no problem, okay? If you have twins that were born on the same day, then, it would be a function if they were all born on the same day. Because, again, single input, single output, but you get the idea. There are always people who are very smart and point that out. Perfect. But if people were born the same day? In that case, single input, single output, that particular case would qualify as a function. But the general idea is 1 input, 1 output. That's it. You don't care what the output is. Doesn't matter if it's repeated. Doesn't matter if it's crazy numbers. Single input, single output, it's a function. Okay. Now that we've gone over the relations that are functions, let's talk about example 4, how to find function values. Okay, pretty straightforward. Again, let's say, for example, I'm told gx equals x squared plus 8x minus 24. And I tell you, there are a couple of ways you can be asked. Like, for example, x equals 1. You just substitute all your x values for 1, and that would, pretty much find the value for the function when x equals a particular value. That's one way, x equals 5. Another way, and you should know this, if they give you a number in the parentheses, that means you just substitute all the possible x values for this number, and that would be the result. Another thing you could do is change it, for another equation, or another term that includes a number and a variable. You just plug it in and distribute properly, no problem. And the trickiest part is, it's not that tricky once you get used to it. If you're given a small polynomial, like say, for example, this. Now, where do students mess up most of the time? When they plug this in a square or a cube or a to the 4th power. Because students, and I've said this multiple times, forget how to properly expand binomials. Please review how to expand binomials properly. Use FOIL, use top to bottom multiplication, use the rule that I've showed you guys. That is number 1 mistake when you're given a small polynomial and you're asked to plug that into your equation, expanding that particular polynomial. So please don't mess out there. Now let's go over the last example, example 5, finding the domains algebraically. Now let's talk about, I'm going to give you guys a crash course on domains. We're going to be seeing domains a lot in this year, and also ranges. Now domain is where your function exists along the x-axis. So for example, if I have this coordinate axis here and I have this function that goes like this, well, my domain would be from 0 to positive infinity. Remember, domain, you only care about the x. The y doesn't matter. These two functions would have the exact same domain, from x0 to positive infinity. I do not care about my y. I repeat, domain only focuses on the x values. Oh my God, it goes all the way up to 4. Does not matter. Don't look at the y-axis. Y-axis does not exist when you're looking at domain. Only x. So from here to here, from here to here. So all these functions have the exact same domain. Where do they change? The ranges. Because the range is the opposite, the output. Only y's matter for range. So this one would begin here and it would end at positive infinity. We'll see that later. This one would begin here and it would end up at positive infinity. This one would end here and end at positive infinity, because it just slowly starts increasing, if you remember square roots. So domains, you only focus on the x, where it exists along the x. Ranges, you only focus on the y's, where you exist along the y's. So graphically, it is quite simple to determine your domain. So let's say, for example, I have this piecewise function. And we'll learn what a piecewise function is later. If I go over, this means it stops existing here and it begins here. Let's assume they are both on the same line. For range, I only care about y. So this arrow means it expands all the way towards negative infinity. So I exist, I stop here, but I still exist up here, and I increase and I continue all the way toward positive infinity. So even though this arrow is pointed diagonally upwards, you're only focusing on the x. Where will that arrow stop along your x-axis? Answer is never. So the range, the domain of this graph or function would be all real numbers, from negative infinity to positive infinity. It exists all throughout your x values. Now, let's go over range. Let's say this value is -3. This y-intercept would be -3, and this value would be +4. The range would be the number 3 and from 4 to, including the 4 because it's filled in, to positive infinity. I only care about the y values when you're looking at range. X does not matter. I exist here at -3 and I exist from 4 to positive infinity. Domain is x, range is y. We will be seeing this a lot more. Start getting used to the ideas of domains and ranges. Now, how do we find the domains algebraically? There are two things we try to do. As I said earlier, with all parent functions except the rationals or square roots, for the moment you can just say the domain is all real numbers in x. It's never going to stop. It exists always throughout your x values. Now, when you're looking at these two possible functions or equations, when you're looking at rational functions, you have to say, when will my denominator, x plus 1, when will this be 0? Because remember, whenever my denominator is 0, 1 over 0 is not a number. Whenever my denominator is 0, there is no answer for that. So that is outside of my domain. So for example, in this case, what you do is you set your denominator equal to 0 and isolate your x. -1, -1, my x is -1. So when x is -1, I would end up with 1 over 0 or not a number. So the domain would be everything except what makes your denominator 0. So the domain would be everything except -1. How do I do that in interval notation? Simple. You begin -infinity. That's a very nice infinity sign. Please don't rip on it. And I get as close to as possible to -1, but I don't include it because at -1 I don't exist. So it is this, or also -1 to positive infinity. So with what you learned in yesterday's video, all this is saying is all numbers from -infinity to positive infinity, that excludes 1. That is a very simple way to just answer this. Any number that isn't 1, because again, I'm getting close to 1, but I can't be 1. And here, I can't be 1. From that point on, I'm going all the way up to positive infinity. So that is one way to answer how to find the domain algebraically. Now note, this one was very simple. Oh my God, you just isolate your x and you're done. Yay! They're not going to be that simple. You will also have to factor. You're going to have to factor many times. So let's say, for example, you're told the following. You could also isolate that one. But you should know that that is the difference of squares. Factoring. Again, I might give a factoring workshop. We'll see. So this would be identical to x plus 4 or x minus 4. That is the difference of squares. And what values would make this 0? If I plug in a -4 here, and if I plug in a positive 4 here. That would make this pretty much not a number. So my domain would be everything except -4 and positive 4. Let's say, for example, I have this one, which is more difficult. Again, that's a quadratic factoring. Two numbers that multiplied give you this, or added give you this. 1 over x minus 4, x plus 1. What would the solutions to this denominator be? Well, no, when x is positive 4 and when x is -1. When you plug those numbers in, you would get 0. And 1, or whatever, over 0 is not a number. So what you're trying to do when you're finding the domain algebraically is see what values make your denominator a 0, and the domain is everything except those numbers that make the denominator 0. If you plug this into your calculator, you will see that at 4 and at -1, you're not going to get an answer back. You're going to get an error if you look at the table. And in the graph, you're going to get an asymptote. We're going to go over that later this year, so don't worry. So again, when you're finding the domain algebraically, if you have variables in the denominator, you're going to have to find the zeros of that denominator, and it's everything except those 0 values. I hope you get that right, or I hope that's clear. You'll be able to ask questions in class. Now, the other parent function that might have, or no, that has a limited domain would be the square root. Because again, the number inside the square has to be greater than or equal to 0. 0 has a square root 0. Any number greater than 0, greater than or equal to 0 has a square root. So let's say, for example, they say x plus 9. What you have to do is change this for an inequality. X plus 9 has to be greater than or equal to 0. Greater than or equal to 0. And then you just isolate normally how you work with inequalities. We might have to go over that, but this case is pretty simple. -9, -9. So x can be greater than or equal to -9. Again, people say, Profe, but that's a -9. I mean, we can't use negative numbers. Remember, this is your input. That's where your domain begins. When I put -9 in here, what is -9 plus 9? 0. And the square root of 0 is 0. So your domain is anything that is greater than or equal to -9. We can put -8 in there. -8 plus 9, you'll end up with square root of 1, which is positive -1. So this tells you what is the smallest value you can use, and anything above that will be part of your domain. So in this particular root, this would be the domain. X is greater than or equal to 9. And I would say, please answer it in set builder notation or interval builder or interval notation. Set builder notation, a set of numbers x such that x is greater than or equal to -9 and x belongs to all real numbers, because you can't include decimals. If I were to use interval notation, I include my -9 in the answer and any number that is greater. And that's pretty much it. We will not be going over example 6 in this video. I'm gonna do another video for that later. Have a great day.